Rates of change, we talked a bit about it already. We're probably now going to look at more in terms of motion, things like that. But remember, our derivative is a rate of change. So anytime you've got a quantity changing with respect to another quantity, then calculus is a great way of measuring it. We also know that the derivative measures the slope of a graph. So therefore, the steeper the curve, the higher the value of the derivative. So in other words, the faster something's going to change. So there's a nice little graph there. So that point P, at that point, what do we know? Well, I know if I was to draw the tangent in, it's going to be positive. So the derivative is greater than 0. And so we know the function is increasing. That's part of our calculus theory that we talked about. If we're at Q, well, Q is a stationary point, derivative 0. So yeah, as I say, stationary. And then of course there's R. And at that point we know it's now decreasing. And so the derivative is negative. Okay, so there's the basic ideas of the derivative. So all right, here's this graph. There's P and Q, 2 points there. Now, the slope of PQ, that particular secant, that would be the average rate of change. So the difference is, with the calculus, we can work out the instantaneous rate of change at that point, which is far more useful when you think about it. I mean, if you're in a car, you're not interested in what your average speed is. You want to know what it is at that particular moment. But if you want to find the average rate of change over an amount of time, then you'd find the slope of the secant that joins the 2 points. So there's R. So as I was saying, that gives you the instantaneous rate of change. So that's the difference between the two. If you want average, you're going to have 2 points, join them up. If you want instantaneous, you're just looking at that particular point, and we'll go and use calculus for that. So that brings us back to something you probably first saw, I don't know, year 7 maybe, travel graphs. You were actually doing calculus and you didn't even know it. Here's a typical sort of travel graph that you would have got. The distance time there. And you would have been asked questions like this. How long was the first stop? So you'd look at the graph and go, where did they stop? Oh, that'd be when the line's horizontal. Well, think about it. If we're now talking about calculus, horizontal, stationary points. Stationary, you stopped. Amazing. Okay, now we can read off our graph, and that was for 30 minutes. When did the coach start to return to the depot? Well, at 1:30, because that's when it's changed from increasing to decreasing. How fast was the coach travelling on the return trip? And that's why we get nice straight lines so you can work it out nice and easily. Oh, distance over time, 100 kilometres per hour. What's the average speed for the whole trip? So they've travelled 400 kilometres and in 6.5 hours, so 61.5 kilometres per hour. But now, because we've got calculus, we don't have to have straight blocky lines and things like that. We can have curves. So we're bouncing a ball and its distance from the ground is graphed there. And there's the equation of that particular graph. So the distance, remember, is the total amount travelled altogether, as opposed to the displacement, which is how far, usually from the starting point, but you could be asked, what's the displacement from another point, but usually it's the starting point. So find the height of the ball after 1 second. Well, we've got a formula we can sub into. I mean, yes, you can read off the graph, but let's use the formula, and we've got 35. At what other time is the ball at the same height? So when else is x equal to 35? Well, just solve this little quadratic. We've got 2 possibilities. Well, we already know the first one was 1 second, so therefore the other one must be 7 seconds. So answer the question. Just don't leave it as t equals 1 or t equals 7. Answer the question they're asking you. So average velocity is the change in displacement, and you get something like that, which looks very much like the slope formula. The derivative measures velocity. Derivative measures slope. It's not a coincidence. So what is the average velocity during the first second? Okay, sub in what we know. After 1 second it was at 35. We're assuming it started at 0. So we get an average velocity of 35 meters per second. What was the average velocity during the 5th second? So be careful. Where's the 5th second? Okay, the first second starts at 0 and goes to 1. So therefore the 5th second must start at t equals 4 and goes to 5. So let's find out where it is. T equals 4, it's at 80. And at t equals 5, it's 75. So the average actually turns out to be negative in this case, because remember, velocity can have positive and negative, just telling you basically the direction that you're traveling. And so negative 5 meters per second. But what's the average velocity over its total 8 seconds in the air? That's sort of like what I was talking about with that other one. You get a really interesting answer where it's actually 0, because you ended up back where you started from. So it's like you didn't travel at all. So average speed as opposed to velocity is when we talk about the actual distance we've traveled, not the displacement. So the average speed when it's during those 8 seconds, well now, distance traveled, it traveled a total of 160 meters in 8 seconds, so that's 20 meters per second. Okay, so there's our first bit.